Welcome back to This Old Protein. I'm your host, Dr. Mills, and in our last video we talked about how the equilibrium constant for a particular reaction is calculated, and we waved our hands and some algebraic magic happened, and we were able to figure out that, well, in this plot that we have here on the right side of the screen, the x-axis is the ligand concentration, and the y-axis represents the fractional occupancy, or how many ligands are in our binding site. So if we have 4 binding sites like we do in hemoglobin, right, having one ligand occupy one binding site means that we're 25%. Or about right here, 0.25. We also talked about an important parameter called KD, and KD is the dissociation constant. The further KD is to the left, right, so the closer it is to the origin, the smaller KD is. The more tightly this ligand protein complex is formed. So if you have a very low KD, say nanomolar or even smaller than that, that means that the interaction between your ligand and your protein is very, very strong, and they will bind with each other even at very low concentrations, which is great if you're trying to design a drug or an enzyme inhibitor or something like that. So there are a couple additional important things that we need to talk about. So, right, if you're doing this experimentally, you would have some test that allows you to measure how many binding sites are occupied. So what you would do is you would start at low concentrations of ligand, and you would run your test, and you would get a number, right? You increase the ligand concentration, you run your test again, you get another number. If you plot all of these things, you should end up with a curve that looks like what we have here on our screen. And if you want to be really accurate and get good numbers and meaningful data, you have to do what's called a linear regression or a nonlinear regression or a least squares regression. These are computationally intensive. They are easy to do if you have the right software and if you're very good at this kind of stuff. So I guess what I'm telling you is there's no way I can expect you to do something like that on an exam. Now, if you notice the second part of this, KD can be determined graphically, right? So if we look at this particular example, you could estimate KD and say that it's about 1 or maybe even 2, whatever these units are. So if these units represent micromolar, I would estimate KD to be around 1 micromolar, maybe a little bit higher, but somewhere around 1 micromolar. To get an exact number, you would have to do that least squares regression that I was talking about. It's not easy, so right, don't worry about that. But you should be able to tell, at least to some extent, with some accuracy, what KD is just by looking at a graph like this. Okay, so if we go on and look at, so here we have myoglobin. Now, myoglobin exists in tissue. It is structurally very, very similar to the monomers in hemoglobin. And the amino acid sequence between hemoglobin and myoglobin is similar, but not identical. Right? So these are two different proteins. They have some similarities in their amino acid sequence, and those similarities are strong enough that they have the same or very similar structures, and they have very similar methods of operation. So if you look at myoglobin here, a few important things to point out. So number one, we're looking at kind of a cartoon view that's designed to give us a rough overview of the structure of the protein. We see a bunch of cylinders and strings in between them. We're not supposed to get detailed information about the structure of the protein from this. We're simply supposed to, like I said, get a rough overview for what it looks like and what the different elements are. So the amino terminus represents amino acid number 1. This is the start of the protein, and this is the amino acid number 1. And we start here. There's a little section of random coil. That's what this string represents here at the end. And then we go into alpha helix A. There's a turn into alpha helix B. And then we go into C, D, E, F, G, and then H. And we reach the carboxyl terminus, or the C terminus, the very last amino acid in the protein sequence. So you can see that this structure is comprised entirely of alpha helices and random coil bits between the alpha helices. Right? So for example, the alpha helix C going into alpha helix D has this CD linker. This is random coil, which means that it isn't really structured. If you were to look at this CD loop or CD linker region in solution, it would have multiple conformations. It would change all the time, kind of like a string fluctuating in a breeze, or like a noodle flopping around in solution. So you could also imagine that this CD linker is fairly large, and if it were to become fully extended, it might even drop down and almost interfere with oxygen binding, right? So the size of this CD loop could be important and could either hinder or help binding of oxygen, especially if there was a little bit of a structural rearrangement with this BC alpha helical region. Okay, so right, that goes back to the idea at the very beginning of this chapter that proteins are dynamic. There is motion involved in proteins, especially in solution. It doesn't adopt this perfectly static structure that we see right now. There are small variations in the angles between helix F and helix E, for example. So almost like a pair of scissors, those two helices might open and close relative to each other. And you can see that the heme group with the iron atom that chelates or binds to oxygen sits in the middle of that heme, and there are these two histidine groups, so His 93 and His 64, that play a role in oxygen binding and heme binding as well. Okay, so right, we can look at the structure of this protein, and we can use our plot of binding site occupancy versus oxygen concentration, and we can see that at 50%, right, so one of every two molecules, or half of the molecules in the solution, half of them are filled. And we can see that the KD is actually very, very small. So this is a tight binding protein ligand complex. The protein holds on to oxygen really, really well. And it only takes a little bit of oxygen in solution to fill up that binding site. Okay. So we've talked about thermodynamics a lot, right? We're talking about association and dissociation constants. The association and dissociation constants are inversely related to each other. They describe the same thing. We like to use KD as our metric because the units make more sense. Right? If we talk about Ka, the units are in per molar, or 1 over concentration. That's fine, but intuitively, it makes more sense if we can talk about molar. Right? So Kd has units of molar, and that's something that we can think of, and it makes sense to us. So we use Kd a lot. It's important to remember that these are all energies and thermodynamic units and thermodynamic concepts. There is also kinetics involved in this, but we are completely ignoring all of the kinetics. So right now, all we're talking about is stuff like delta G, delta H, delta S, the equilibrium constant. And just to give you a rough idea, we would typically quantify or qualify these binding interaction in terms of how strong Kd is or how small Kd is. So in this case, we're saying that anything with a Kd less than 10 nanomolar, we would call that a strong binding complex. Anything with a Kd greater than 10 micromolar, 10 to the minus 6, we would call that a pretty weak binding complex. Right, so there's a huge range of binding affinities that we can talk about, and they're all useful for different things. So just to give you an example, we can talk about enzyme substrate binding. That ranges typically in the micro to millimolar, so 10 to the minus third up to 10 to the minus 6, somewhere in that range. We call these low affinity or weak binding complexes. And I think this is important because if an enzyme substrate or an enzyme ligand complex is too tight, there's no way for the reaction to happen, so this enzyme won't actually catalyze a reaction if the interaction is too strong. Something like an antibody and its antigen, on the other hand, has a very strong 10 to the minus 12, 10 to the minus 9, somewhere in that range. So a very strong binding affinity. And that's important because the whole idea of an antibody is to grab onto something in your body that shouldn't be there so that your body can then identify it and attack it. So if that interaction was very weak, it wouldn't be very useful, right? The antibody would fall off of the antigen and your body wouldn't know what to attack. Okay, so I want to talk quickly about these two types of models that a lot of people historically have used to describe protein ligand interactions. So this first one is the original. It's probably the one that you've heard the most about. It's probably the one that most people use when they're talking about a protein interacting with a ligand. I like this analogy because it's simple. It's easy to think about. And this is the lock and key mechanism. So the idea is that you have a protein represented by this, I don't know, brownish S-curve thing. And then you have a ligand represented by this pink cylindrical thing. And if you look at the protein, it has a curve that is exactly complementary to the curve on the ligand. So the lock and key mechanism says that the protein already has the exact structure, size, shape, charge, hydrophobic, hydrophilic interactions required to interact with a ligand. And this is an equilibrium interaction. You got the protein, you have the ligand, you put the two together and you end up with a complex, and that complex can then dissociate and form the individual components again. Right, so the lock and key model is very simple to understand. If your grandparents were to ask you about protein interactions, you would probably tell them the lock and key model just because it was easier to understand and you can show them examples for it. Now, Even though that's the easy one, it's not necessarily the accurate model that a lot of people like. So induced fit is the preferred model here. In the induced fit model, we have, again, our protein represented by this brownish thing. We have our ligand, again, represented by this pinkish thing. And we can see that the protein and ligand are not complementary at all. There is no indication that the shape is correct. There is no indication that the size of the binding site is correct. And there's also no indication that the electrostatics or hydrophobic hydrophilic interactions are in the right place to allow this interaction to happen. Yet, when you add the protein and the ligand, you still end up with this complex. So they must interact. So the induced fit mechanism says that the binding site will change to accept the ligand. Right? If you want to think about this in more concrete terms, you can talk about, let's say your pillow. Right? So the pillow that you have on your bed that you sleep on. If your pillow was a lock and key pillow, it would have a perfectly contoured hole in the center of the pillow that was specifically designed for your head. It would make space for your nose, your chin, the size of your forehead, the size of your head, your hair. All of that stuff would be taken into account. And if you lay on your right side when you sleep, you put your head in this groove and it fits perfectly every time. Now, I think you can immediately see the problem here. If you were to, say, flip over to your left side, or if you were to lie on your back or your front, you can see pretty quickly that this lock and key mechanism is not going to work. It's not going to be super comfortable for you. So a pillow is more like an induced fit, right? It doesn't matter how you lay on your pillow. The pillow will conform to fit around your head. Okay.